This is section 12.8, part 3, and we're now going to look at some applications of optimization. In this first one, we'd like to know what point on this plane, x plus y plus 4z equals 8, is closest to the origin. So what we're really trying to do here is to minimize the distance. From some random point x, y, z on this plane to the origin 0, 0, 0. Okay. Well, in order to do that, I'm going to start with my distance formula. It would just be the square root of x minus 0 squared plus y minus 0 squared plus z minus 0 squared. Kind of a boring point this time since we're going to the origin, but of course no matter what point we had here, we can plug that into our distance formula. So that's just the square root of x squared plus y squared plus z squared. All right, we know now that to find the maximum or minimum of something, we need to set both the first derivatives equal to 0 to find our critical point. The problem we have here is hopefully a somewhat familiar one from Calc 1. We have too many variables, right? When we've done our optimization problems in the last video, we only had 2 variables. They happened to have been x and y. Same process would have worked no matter what variables I use, but I only want 2 of them. So in this case, let's go ahead and solve using the plane equation for either x, y, or z, it doesn't really matter, and then we'll substitute into this formula. And in this case, I'm going to go ahead and just solve for x. X would be 8 minus y minus 4z. And so plugging that in, we have an equation now in just 2 variables. So that's a start. All right, the next step should be to take the derivatives with respect to, in this case, y and z happen to be our variables, and set them equal to 0. But I'm going to ask you to recall another kind of common strategy that you may have used in Calc 1. Ultimately, I really want to minimize the distance, which is the square root. But if I just minimize the stuff that's under the square root, I would be able to minimize the entire square root. So I'm going to define a different variable. I'm just going to call it capital D as little d squared. And that allows me to get rid of that square root. So if I minimize d, I will also minimize little d. And it's much prettier. I don't have to deal with that square root. All right, so let's find critical points. The first derivative, let's do the derivative with respect to y first. And I'm just going to use a chain rule here. 2 times all that to the first times negative 1 plus 2y is going to give me, let's see, I'm actually multiplying by negative 2, so negative 16 plus 2y plus 8z plus 2y. You know what, that extra plus 2y, I'm going to cheat here. I'm just going to make that a 4. So there's my d sub y. And I want that to be equal to 0. All right, let's do d sub z as well. Start out the same way. And let's see, chain rule this time is going to give me a times negative 4 plus 2z. And I'm multiplying by negative 8. So that'll make that a negative 64, a positive 8y, a positive 32z, plus those extra 2z's is actually going to make it a positive 34z. And again, that's dz, but I would like to set that equal to 0 to find my critical points. So let's see, I've got these two equations here. This first one, if I play with that one a little bit, it would say 4y plus 8z equals 16. So dividing by 4, y plus 2z is 4, and y is 4 minus 2z. And I'm going to plug that into the second one. And let's see here. I'm going to get negative 64 plus 32 minus 16z plus 34z equals 0. What is that? Negative 32. I'll move that to the other side. And that would be an 18z. So z is 32 over 18, 16 over 9. All right, we can go back and get the y just by plugging in here. So y would be 4 minus 2 times 16/9. And that's 4/9. And then I can actually go back and get the x all the way back up here, right? We had a expression for x. So let's do that. If I plug in there, x was 8 minus the y value, 4/9, minus 4 times the z value, 16/9. And that also gives me 4/9. So, assuming this is a minimum, which I actually haven't verified yet, but we can talk about that in a minute, but assuming that this is actually a minimum, I have now found the point that's closest to the origin, but still on that plane. The point would be 4/9, 4/9, 16/9. Before I circle that and call it good for my answer, let's go ahead and do a quick test. Let's make sure that our found solution really is a minimum. To do that, I need the second derivative test. So d sub yy is just 4. D sub zz is 34. And d sub yz is 8. So, sorry, I'm using d in two different ways here. We can call this something else. I'll just call it the test for right now, because I've already been using the letter d. Would be the product of these minus the square of that one. And that is 72. So it's positive. Notice that the d sub yy is like the d sub xx here, and that's also positive. So positive, positive does give me the minimum that I was looking for. And I can now say, yes, I'm confident that that point is the one that minimizes the distance, or is closest to the origin. As you can see, the algebra on these does get to be a little bit ugly. It's not exactly difficult, just time-consuming. So on the next problem, I think we're going to see an even uglier function, and I'm actually going to make use of some more technology to solve that one. So, in example 6, we have a lidless box made using 2 square meters of cardboard. Find the dimensions of the box with maximum volume. So let's see, I've got a box here. And normal dimensions, we just call them x, y, and z. And ultimately, I'd like to find the dimensions of the box with maximum volume. So my goal is to maximize the volume, x times y times z, length times width times height. We have that familiar problem. To find a maximum or a minimum, I should do the two first derivatives. But the problem is right now I have three variables. So I'm going to need to reduce or get rid of one of the variables. And we can use that, or we can use this extra information about the fact that we used 2 square meters of cardboard to create this box. So the surface area of the box is 2. Surface area would be the bottom, xy. There is no top, remember, it's lidless. There's a front and a back that would both be x times z, so 2xz. And there's two ends that would be y times z. So 2yz. And that all has to equal 2. Once again, our goal is going to be to solve for one of the variables. It doesn't make a whole lot of difference which one. I'm going to go ahead this time and let's see here. Which one should we solve for?